Hi students, in the last class we have seen about electric potential. In the today's session we are going to see about the electric potential due to an electric dipole. Before moving to the topic, we want to know about what is meant by electric dipole. Electric dipole is nothing but two equal and opposite charges separated by a very small distance. It constitutes an electric dipole. For example, if we consider plus q and minus q separated by a small distance 2a, then it constitutes an electric dipole. In the electric dipole, we want to find the electric dipole moment. What is electric dipole moment? It is the product of any one of the charges into the distance between the two charges. It is denoted by the letter P. P is equal to Q into 2A, where Q is one of the charges and 2A is the distance between the two charges. This dipole moment has a direction from negative to positive charge. The electric potential due to an electric dipole. Consider an electric dipole consists of minus q and plus q separated by distance of 2a. Consider a point P at a distance of r from the midpoint of the dipole. We want to find the electric potential at this point. And also consider R1 is the distance between the charge plus q and the point P, and R2 is the distance between the charge minus q and the point P. So these are the considerations. Now we want to find the electric potential at that point. To that, we want to consider the potential at P due to plus q and minus q separately. And after that, we want to find the total potential at P. The potential at P due to plus q is given by V1. V1 is equal to 1 by 4 pi epsilon naught q by R1. Similarly, the potential at P due to minus q is given by V2. V2 is equal to minus 1 by 4 pi epsilon naught q by R2. Then we can find the total potential at P. The total potential at P is V. V is equal to V1 plus V2. Therefore, V is equal to 1 by 4 pi epsilon naught q into 1 by R1 minus 1 by R2. So this is the total potential at P due to the entire dipole. Then we want to find the 1 by R1 and 1 by R2 and substitute in the expression to get the net result V. And also consider the distance of the plus q and the point P is R1 and the distance of the minus q and P is R2. Therefore, we want to find the total potential at P. If you want to find the total potential at P, we want to find the potential due to plus q and minus q separately. Then we can find the total potential at P. As the next step, we want to find 1 by R1 and 1 by R2. In order to find 1 by R1 and 1 by R2, we can use cosine law. We want to apply the cosine law separately for R1 and R2. First we can apply the cosine law for R1. Then R1 square is equal to R square plus A square minus 2AR cos theta. R1 square is equal to, in the right hand side, we can take R square outside the bracket. Therefore, R1 square is equal to R square into 1 plus A square by R square minus 2A by R cos theta. Now, if you see that R is very greater than A, therefore, we can ignore the second term in the expression, that is A square by R square. After neglecting the second term, we will get R1 square is equal to R into 1 minus 2A by R cos theta. Now we can find the square root. Therefore, R1 is equal to R into 1 minus 2A by R cos theta whole power half. Then finding the reciprocal, we will get 1 by R1 is equal to 1 by R into 1 minus 2A by R cos theta whole power minus half. Now we can use the binomial theorem to expand the entire equation. If we expand, the higher order terms can be ignored. After ignoring the higher order terms, we will get 1 by R1 is equal to 1 by R into 1 plus A by R cos theta. Now we can find 1 by R2. To find 1 by R2, we can use cosine law for R2. If we use cosine law, then R2 square is equal to R square plus A square plus 2A by R cos 180 minus theta. Then we can get R1 square is equal to R square plus A square minus 2AR cos theta, because cos 180 minus theta is minus cos theta. Then we can take the R square outside the bracket. Then we will get R2 square is equal to R square into 1 plus A square by R square minus 2a by r cos theta. Now we can ignore the second term as we already told that r is very greater than a. We will get r2 square is equal to r into 1 minus 2a by r cos theta. Finding the reciprocal, 1 by r2 is equal to 1 by r into 1 minus 2a by r cos theta whole power half. Then we will get finally 1 by r2 is equal to 1 by r into 1 minus a by r cos theta. Now we can find the net potential. We already found that V is equal to Q by 4 pi epsilon naught into 1 by R1 minus 1 by R2. Substituting the value for 1 by R1 and 1 by R2, we get V is equal to Q by 4 pi epsilon naught 1 by R into 1 plus A by R cos theta minus 1 minus A by R cos theta. So removing the bracket, we will get 1 by 4 pi epsilon naught Q by R into 2A by R cos theta. Finally, we will get V is equal to Q by 4 pi epsilon naught R square 2A cos theta. This Q into 2A can be replaced by P because that is dipole moment P. Therefore, we will get V is equal to 1 by 4 pi epsilon naught P cos theta by R square. It is possible to express this in vector notation, that is we can replace P cos theta. If you replace P cos theta by P vector dot R cap, then we will get V is equal to 1 by 4 pi epsilon naught P vector dot R cap divided by R square. This is in the vector form. Since P is the dipole moment, it is a vector quantity. So it is possible to express this in terms of vector and unit vector. If R cap is a unit vector for the line joining the midpoint of the dipole and the point P, then the entire expression can be written as 1 by 4 pi epsilon naught P vector dot R cap by R square. So this is the final result. From this final result, we can study the special cases. What are the special cases? From the results obtained, we can have three cases which depends upon the theta. Special cases, case 1. In case 1, theta is equal to 0. It means that the point lies on the right side of the plus q charge. If it lies on the right side of the plus q charge, then the potential V will be equal to 1 by 4 pi epsilon naught P cos 0 by R square. Cos 0 is equal to 1. So the result will be V is equal to P by 4 pi epsilon naught R square. So this is the case 1. And in case 2, theta is equal to 180 degree. It means that the point P lies on the left side of the minus q charge. If it lies on the left side of the minus q charge, then cos 180 we want to keep. Therefore, V is equal to P cos 180 by 4 pi epsilon naught R square. Cos 180 is equal to minus 1. Therefore, V is equal to minus P by 4 pi epsilon naught R square. Then case 3. Let us consider the point is on the equatorial line. If the point is on the equatorial line, then theta is equal to 90 degree. If theta is equal to 90 degree, then V is equal to P cos 90 by 4 pi epsilon naught R square. Cos 90 is 0. Therefore, the expression becomes V is equal to 0. That's why if the point is on the equatorial line, then the potential at P due to the plus q and minus q charge will be 0. There are some important points due to the electric dipole. The electric potential due to the point charge falls off with respect to 1 by r, where r is the distance of the point from the point charge. Similarly, the electric potential due to the entire dipole falls off with respect to 1 by r square, where r is the distance of the point from the midpoint of the dipole. If we compare the electric potential due to the entire dipole with that of the electric potential due to a point charge, the electric potential due to the entire dipole falls off very rapidly and faster than that of the electric potential due to the point charge. The second point is the electric potential due to a point charge is spherically symmetric. That is, it depends upon the distance of the point from the point of the charge. And the electric potential due to the entire dipole is not radially symmetric, and it depends upon the angle between the line joining the midpoint of the dipole and the point. Point number 3, the dipole potential is axially symmetric when compared to the electric potential due to the point charge. If you consider the radius vector is rotated with theta fixed, the points on the cone will be at the same potential. That's why the electric potential due to the entire dipole is axially symmetric. We came to the end of the session and I hope you understood about the electric dipole and electric potential due to the dipole. In the upcoming session we are going to see about Weyer's law. Thank you.